Hello everyone, this is Taylor walking through question 7 of the Spring 2019 MAS 1 exam. Let's get started. Given the following information. In a toolbox there are two types of components that all perform the same function. There are 4 components of type A, each with reliability 0.6. There are 20 components of type B, each with reliability of 0.3. All components are independent. Using only components in this toolbox, you want to construct a parallel system with reliability of at least 0.995. Calculate the minimum number of components needed to create this system. For this problem, you need to know 2 things. So first off, what reliability means. So that's just saying what's the probability of success, whether it be for a part or for the system as a whole. It's just the probability of something working. And second, you need to know what is meant by a parallel system. So I have 2 examples here. So there are series systems and there's parallel systems. So for a series system, you might think of this as whether or not your light is turned on. And we'll say if the light is on, then that is reliable or a success. So, first I need to pay my electricity bill. If I don't, there won't be electricity to power the light. After I do that, I also need to turn the light switch on. And then finally after that, if someone were to have cut the wires that lead to the light bulb, even if I paid my bill and turned on the light, if the cables are cut, the light won't turn on. So this is an example of a series system where all the subcomponents within a series need to be working in order for the overall system to function. Separately, you could have a parallel system. So if you were wearing pants, I hope you are if you're watching my video, you could be maybe are really worried about your pants falling off, and so you wear both suspenders as well as a belt. If you were to do this, you can imagine that, if all of a sudden your suspenders broke, your pants aren't going to fall down, you're still wearing a belt. Or if your belt failed, all of a sudden your pants aren't going to fall down, you're still wearing suspenders. So this is what is meant by a parallel system. You only need one of the components within a parallel system to function in order for the overall series to function. So that's what's meant by a parallel system. The one thing I'll add, it's not relevant to this problem, but you can obviously have subcomponents within systems. So you can have one of, maybe this light switch here. If you zoom in, you could break it into a parallel system, and there's multiple things that go into that. Or vice versa, you could have a series system as a subcomponent of a parallel system. But these are just really simple examples to illustrate what is meant by these terms. So, jumping into the problem, we have 4 60% reliability components, 20 30% reliability components, and we're trying to up our reliability to 99.5%. So I prefer, it's easier to think of things in terms of failure when dealing with a parallel system. And the reason why is there's only one way the system can fail, and that's if everything fails. If you're dealing with successes, there's so many different ways. You can have one of the components work, or you can have 2 components of them work, or 3 of them can work, and there's all those different permutations. So with parallel systems, you actually want to work with failure because it's just easier. So the first step is just, we don't want a system with reliability of 0.995. We want a system with a chance of failure of 0.005. So that's why we do that here. And then that really simplifies our calculation. There's only one way a system can fail. So the next thing to do is we're trying to minimize the number of components we need. So if we want to minimize the number of components we need, we want to become reliable as quickly as possible. And so that's your hint that before you even touch these type B components, you want to use up all of your type A components. So what you could do is say, I want to see, is one type A component sufficient? No, 0.6 doesn't reach our 0.995. Are 2 of type A components going to work? So here you'd want to do the probability of failure and and check if 2 meets it, and 3 meets it, and if 4 meets it. But the fact that they're a type B, I chose to kind of assume that chances are I'm going to need at least 5 components. And then if I'm wrong, I can go back and test that, but I figured it was a safe assumption. So what I did was I just jumped straight to what's the probability that those better components fail is 0.4, because that's 1 minus that 0.6 probability of success. And then there's 4 of them, and since they're independent, you can just multiply those probabilities. So that's the probability of all 4 of those things failing. I then want to add on the worst components, which have a probability of failure of 0.7, since they have a reliability of 0.3. And I'm going to put them to the power of x, because I want to solve for how many of those components do I need. Solving for x to get this failure rate of 0.005, I end up getting that x is equal to 4.5. So what this means is I need 4 of that type A component, the better component, and I need 4.5 of the worst component. Now, 8.5 is a troublesome area, because it would be nice if it was something like 9.5, because then you could just answer E. But since whether we round down or up will affect whether the answer is D or E, we have to think about that. So to think through, why do we need to round up? If you only used 4 instead of, so you round that x down to 4, we can then plug those values in here, and we're going to see that the chance of the system failure is going to be higher than 0.005. And that is unacceptable, because we need a failure rate of 0.005 or lower. So we can't round down, we have to round up, and that's how we get up to needing 5 of those components, of type B components, which results in a total 9 components needed. And again, that means our final selection is E. Thank you for watching, and if you find these videos helpful, please consider subscribing. Thank you. Have a good one.